Hello, Dr. Diaz here with the first lecture video for chapter 4. And in this chapter, we're going to talk about calculations in the chemical equation. So these calculations are going to relate a lot to the ones that we did for chapter 1. This is very important for you to keep in mind because all of the stuff that we did with dimensional analysis in chapter 1, meaning going from centimeters to yards, or from meters cubed to centimeters cubed, or that kind of stuff, in here is going to happen again. But instead of doing that, what we're going to do is something like grams of this to moles of this, or atoms of this to moles of this, or moles of this to moles of that. Okay, so it's going to be just in converting chemical units rather than standard units for measuring distance or temperature or anything like that. Okay, so we're going to go ahead and start going into the chemical realm of conversion of units. Okay, so of course we have to start with some concepts of these units that are commonly used in chemistry. So one concept that is very, very common in chemistry is the concept of a mole. Okay, so what is the origin of this concept? Well, atoms are very, very, very small. So much so that if you have an atom of carbon 12, it actually has a mass of exactly 12 atomic mass units, okay? So AMU stands for atomic mass unit. Now, what is an atomic mass unit? Because we're used to like, okay, but how much is that? Well, an atomic mass unit is 1.66 times 10 to the power of negative 24 grams, okay? So that's a whole bunch of zeros, and then finally you have a 112. Good. So the periodic table will give you your masses in AMUs, okay? So we can go ahead and take a look at the masses in the periodic table just for a second. And in here, you see that the mass of carbon is 12.011. But again, that is not the mass of carbon 12. That is the average mass of the isotopes of carbon, of which you have carbon 12, carbon 13, and carbon 14. Remember, that's something that we actually saw on chapter 2. But whatever the case, this number in here is 12.011 atomic mass units. That is the mass of a weighted average atom of carbon, okay? Good. So we can go ahead and express again any mass from atomic mass units. We can go ahead and get it in grams. Okay, so for instance, from the periodic table, we can quickly see that the atomic mass of fluorine is actually 19.00 atomic mass units. So using the conversion that we had before, this one right here, AMUs to grams, we can go ahead and figure out, well, how many grams is one atom of fluorine. So as you can see, every time that we're looking for the mass of just the one atom, it's always going to be a very, very minute quantity. So, well, obviously we're chemists. We're not really working all the time with one atom. Actually, we rarely do so. Every time we work with grams of stuff, like actual grams, not 10 to the power of negative something, but like 1, 2, 3, 20, or something along those lines, okay? So, well, of course, it's then more convenient to work in those units like big grams, okay, instead of this very, very little things. And this is where the concept of mole arises, because then we need actually, since we know that the atom is very, very small, then let's go ahead and group all of these atoms, very, very small atoms, a lot of them. Let's go ahead and group them into one term. And this term is called a mole, okay? So 1 mole of atoms is going to be equal to 6.022 times 10 to the power of 23 atoms, okay? So this is actually, the origin of this number is exactly how many atoms of carbon 12 you have in 12 grams of that element. So if you have 12 grams of carbon 12, it will have this many number of atoms. If I would have been the one defining this number, I would have defined it. I mean, it's a definition. You can do whatever you want with it. Okay. So I would have defined it like 110 to the power of 20. Let's call that a mole, or 110 to the power of 23. But it's defined in terms of the 12 grams that I was mentioning. Okay. So therefore, we have this kind of weird number. Good. Just for you to know, Mole Day is October 23rd. And no, I do not celebrate Mole Day, but many of my fellow chemists actually they do. Okay. So this number is called Avogadro's number. It is named after Avogadro, Amadeo Avogadro, which is an Italian scientist that did some preliminary work to get to this number, okay? But he actually didn't come up with the number. The number came out centuries after he passed, okay? So we're actually going to see Avogadro's name when we go ahead and do the gas chapter in the future. Good? Okay. So many people are confused. Okay, but what is a mole? Well, I mean, a mole is just one mole is this much. Okay, so we are actually used to that kind of thing. Don't we say like we have a pair is two and a quartet is four and then a dozen is 12? Same thing. A mole is just 6.022 times 10 to the power 23. Of what? Of whatever. You can have a mole of atoms, a mole of stars, a mole of shoes. Well, but of course, if you want to go ahead and think of a mole of shoes, I know probably some ladies would like to do this, but I mean, it's just almost an infinite number of shoes, okay? Not even in the entire world history does that many shoes have been even made, okay? So it's a ginormous number. And then, of course, the ginormous number is not going to be able to be applied only but to very little things. Good. Okay. So what is the relationship between uh, the moles that I was talking about and the AMUs? How can we go ahead and relate them? So here is a very interesting calculation. So if you go ahead and I mean, we already said that fluorine has an atomic mass of 19 atomic mass units. So this is per atom of fluorine. So we can go ahead and find how many grams we have there. This is something, a calculation. This part was done a couple slides ago. And then, but after that, we can go ahead and find actually how many moles of fluorine we're actually having, okay, per gram of fluorine. So notice that the only units that are not canceling is grams of fluorine per mole of fluorine, okay? So after you do this calculation, well, you get back the 19.0, but notice the units is not AMUs anymore, okay? This is grams of fluorine per mole of fluorine. More commonly said, 19 grams per mole of fluorine, or just straight 19 grams per mole. So then the number that we read in the product table for the atomic mass is also the molar mass. And what is a molar mass? The molar mass is just simply the mass in grams of a mole of atoms. So the periodic table is providing us with some dual information. This number that we have in here for fluorine, it has one more significant figure in here. That's why it's not exactly 19. This number that we have here, okay, could be read in two ways. The atomic mass is 19.00 AMUs, or 18.998 if you want to put an additional significant figure, or it could be read as 18.998 grams of fluorine per mole of fluorine. Good. So notice that the number is the same, but the thing that actually changes is the unit that we're using. Okay. Good. So we are going to be using all of these things that we just mentioned as conversion factors. Remember, in the past, as I said, we used to go ahead and convert grams to milliliters. What did we use for that? Well, we use density, okay? But now we're going to be able to convert atomic masses to grams using converting between AMUs and grams, the conversion factor that we saw, the one of the times 10 to the negative 20 some grams is equal to an AMU, okay? And we're going to be able to convert from number of atoms, ions, molecules, to moles of such things, okay? And here it says atoms, but it could be of whatever of the minuscule kind of atomic scale, okay? And finally, the molar mass would be able to go ahead and help us to convert grams per moles. And then, of course, we could go ahead and go, if we can go from, let's say, AMUs to grams, well, then later on, we can go from grams to moles. So we could go from AMUs to moles, which is something that was done in the slide. So it's very similar to when we did in class before this conversion factors. And instead of having something being converted, a quantity being converted through a conversion factor, you can go ahead and do multiple conversion factors one after the other to go ahead and do multiple conversions. So we're going to be doing exactly the same thing. So as I said, this class builds up, and we're going to use the concepts that we use in chapter 1 very much so for this particular chapter, okay? So we're going to start doing here an example, and this one says calculate the number of mole, sometimes it's actually said number of moles, of sulfur represented by 1.81 times 10 to the power of 24 atoms of sulfur. So let's get this out of the way and go ahead and write it in here. So we have 1.81 times 10 to the power of 24 atoms of sulfur. And our goal is going to be to go to moles of sulfur. So again, this is the quantity that we have. How do we know it's a quantity? Because it just has the one unit. So our conversion has to start with that. So we start with the 1.81 times 10 to the power of 24 atoms of sulfur. And our goal is to use the conversion factor that takes us from atoms of sulfur to moles of sulfur. Do we have such a conversion factor? Yes or no? So what is the equivalence between atoms and moles of whatever? Well, we know that is Avogadro's number, okay? So Avogadro's number, you have to memorize it. Good, so keep it in mind. 6.022 times 10 to the power 23. So in 1 mole, we have 6.022 times 10 to the power 23, okay? So keep that in mind, it's important. Then what's going to happen? The atoms of sulfur are going to cancel with the atoms of sulfur, and only the moles of sulfur will go ahead and survive. So then after you go ahead and you do this calculation, this is going to give us 3.01 moles of sulfur. Good. So this is our final answer. Just a quick noting here. Every time when we're doing conversions that involves multiplications and divisions, I've said this in the past, but it's good to have a little review. The number of sig figs that you have in here will be equal to the number of sig figs that you have in the answer. And the reason for this is very simple. We always assume that conversion factors are exact, meaning that they have infinite number of significant figures. So since we're doing multiplication division, then the rules that apply is we go by the number with the least number of significant figures. Well, the only number that we have that has not infinite significant figures is this one, okay? So then we just go by the significant figures of this number. And this will apply for every kind of conversion that we use using this method, okay? Good. So here is, again, the solution to that. You can go ahead and review it. It's essentially the same thing that I just did, okay? And we're going to do now another example. This one says, what is the mass in grams of 3.01 moles of sulfur? Notice, of course, that this problem is very much related to the previous one, okay? Because if you remember, the previous problem was actually converting some actually some atoms of sulfur to some moles of sulfur. Now we're going from moles of sulfur to mass of sulfur. Good. So let's go ahead and do that. So we're going to start from the 3.01 moles of sulfur, and our goal is to go ahead and go to grams of sulfur. So between moles and grams, what are we talking about? Grams per mole. That thing was called a molar mass. Where do we find a molar mass? Oh, in the periodic table. So we go to the periodic table and we look for sulfur, and right here you have it. The molar mass of sulfur is 32.06 grams per mole, okay? So we go back to our problem and we make a quick note of that. 32.06 grams of sulfur per moles of sulfur. Good. So, well, all we have to use is the molar mass that we have here to go ahead and convert this thing to grams. So we set it up. 3.01 moles of sulfur times, get rid of the moles of sulfur, obtain grams of sulfur. So basically 1 here and 32.06 in here. Okay. And then my units canceled properly. And now I have grams of sulfur. And the answer for this thing is going to be 96.5 grams of sulfur. And please check that your answer goes ahead and makes sense. We roughly have 3 moles, and this number is roughly 30. So if we have about 30 grams per each mole, well, if we have 3 moles, we should have around 90 grams. This is exactly what we have. Why do I tell you this thing? Remember, the enemy betrays, okay? And you never know what kind of number it's going to give you, but it's certainly going to give you a number. So we have to check that that number is indeed reasonable. Okay, so again, the problem is in here for you to check. So let us go ahead and now do it, another problem, very similar to the ones that we've been doing. But now we're going to do a multi-step problem. We're going to go straight from atoms to grams. Notice that on the previous one, we did that, but we did it stepwise. Now we're going to go ahead and do it all in one setup. So let's go ahead and set it up. And what we have is that we're given with 1 gram of sulfur, and the goal is to go ahead and convert it to atoms of sulfur. In the previous case, actually, we went in the other direction from atoms to grams in the 2 steps. So we're going to need a couple pieces of data, okay? Just go ahead and remind us what they are. Remember, Avogadro's number is 6.022 times 10 to the power of 23. In this case, we use atoms per 1 mole, okay, of atoms. Good. And then, of course, we're going to use atoms of sulfur. And then we set 32.06 grams of sulfur per 1 mole of sulfur. So all we have to do is arrange these conversion factors after, of course, our quantity that we're giving here in such a way that the units cancel and we get from grams to atoms, okay? So let's go ahead and do it. We start with the 1 gram of sulfur. And now we do as always. Please do not write any numbers yet. Let's go ahead and take care of the units. From grams of sulfur, which we can find here, we can go to moles of sulfur. Okay, so let's do that. Moles of sulfur. And then finally, from moles of sulfur, okay, that would be the moles here, because we already used this. Then we can go to atoms. So then atom of sulfur. And now we go ahead and we filled out our numbers. So this is the 32.06 goes with the grams. And the 6.022 times 10 to the power of 23 goes with the moles, okay? And ultimately, this gives us 1.88 times 10 to the power of 22 atoms of sulfur. Does the number make sense, yes or no? Well, look at the molar mass. The molar mass of this thing is 32. So 1 full mole will have 30 grams. Well, I mean, we have just the 1 gram, okay? So it makes sense that this number is actually less than Avogadro's number, good? And just a power of 10 less, okay? Because we're going from 10 to ones kind of thing, okay? So the answer does make sense, which is good, okay? Good. So here you have something that is taken directly from your notebook. I mean, it's telling you steps to do. I wouldn't recommend you to memorize these steps. Let me tell you something. The first thing that fails for everyone on every test is your memory. Memory is going to fail you big time. Your logic at the beginning may be shaky, but once you go ahead, oh, I'm doing the test, then you go ahead and your logic is always with you. Good. So if we do that logical arrangement of the units, keeping in mind what conversion factors we have and what quantity we start with, we are going to be able to come up with these pathways all the time. We do not have to memorize them. It's a recipe for disaster. Unfortunately, your textbook puts a lot of emphasis on this kind of thing, okay? So again, memory, in my experience, is very, very, very bad companion for going ahead and doing these problems. So in here, you have the problem again for you to review, essentially the same setup that we did. And now we're going to do some practice calculations. So as I told you before, this is the moment where you go ahead, you sit down, you pause the video, and you do all of this on your own. We have done examples that cover every single one of these, but at this point, it's actually very, very useful for you then to go ahead and sit down. You pause the video, try to do them on your own, give it a couple minutes, 5, 10 minutes or something like that, like 2 minutes per problem or so. And then after that, come back, check it out. And if you're good, then you're good. Okay. And if you're not, then you probably are able to go ahead and fix what was wrong after finishing watching the video. Good. So we're going to start with number 1. And then for number 1, we have that we have the 1.7 moles of boron, and we want to make it into atoms of boron. So we do 1.7 moles boron times, we get rid of the moles of boron, and can we go ahead and go straight to atoms of boron? And the answer is yes, because for this we use Avogadro's number. Okay, so units cancel, you get atoms of boron, perfect. And the calculator is going to go ahead and give you 1.02374 times 10 to the power 24. But how many sig figs we need? Only the 2, okay? So then we go ahead and we make this into 1.0 times 10 to the power of 24 atoms of boron. And it makes sense because it's a little over a mole, so it should be greater than Avogadro's number. Okay, so this is our answer in here. And then we go for number 2. Number 2 says, find the mass in grams of 2.5 moles of sodium. And then we go ahead and we have the 2.5 moles of sodium. And we want grams of sodium. So we start with the 2.5 mole of sodium. Again, as I said before, you can go back and forth between these two. Doesn't really matter. They're the same thing. So then we get rid of the moles of sodium. And we writing here grams of sodium. So where do we get the number that we need? Grams per mole. Go back to the periodic table. Whoop. And for sodium is 22.990. So 22.990 grams per mole. So again, units cancel, grams of sodium. And after that, we have that the calculator gives you 57.4 something, but that goes ahead and rounds to 2 significant figures as 57 grams of sodium. Number 3. This is a little more complex. We want to go ahead and go from 5 grams of aluminum to the number of atoms that you have in there. Calculate the number of atoms in 5 grams of aluminum. So, of course, this is atoms of aluminum. So then we start with the 5 grams of aluminum. And, I mean, it would be nice if we could go directly from grams of aluminum to atoms of aluminum, but we can't. We know that from grams we can go to, as you can see up here, moles. And then from the moles, we're going to be able to go finally to the atoms. Good. Okay. So grams per mole, every time that you read that, or moles per gram, whatever, depending on which way the the conversion factor is written, you're going to always find that thing is the molar mass. Find it in the periodic table. So 26.982. So then we go here. 26.982 goes with the grams, and the moles is 1. And then the moles is 1, and then the atoms is 6.022 times 10 to the power 23. Notice one thing in all of these conversion factors, the moles for both the molar mass and the conversion factor with Avogadro's number is the one that goes with the 1 all the time, okay? So that makes it a little easier to remember. So then this cancels, and then we get atoms of aluminum. So then the atoms of aluminum, calculator gives you a whole bunch of numbers, okay, 1.1159, something like that, but that rounds to 1.1 times 10 to the power of 23 atoms of aluminum. Good. And then for the last one, we have that we want to calculate the mass of 5.0 times 10 to the power of 6 atoms of gold. So we have 5.0 times 10 to the power of 6 atoms of gold. And we want to know grams of gold. So this is another multi-step problem because we have to start from the 5.0 times 10 to the power of 6 atoms of gold. And then we have to eliminate those atoms of gold. And from atoms, mole. And then from moles, then we can get to grams. So the numbers are, remember, the moles are always 1, so the atoms were 6.022 times 10 to the power 23. And the grams of gold, we go to the periodic table. Gold is right here, 196.97. So 196.97, and that gives you 1.6 times 10 to the power of negative 15 grams of gold. And I know you have 5 million atoms of gold, okay, which seems like a large number, but don't forget, I mean, atoms are very small. So the mass that we're going to get is not really that big. Good. For the mass to amount to something tangible, we need to have something in the order of a full mole. This is very far from a full mole because this is just a power of 6. So we're still missing 17 powers of 10 to get to something really tangible. So this mass is very minuscule as we're expecting, okay? Good. So to wrap up this, I will show you something that I want you to see and then to forget. This is very much what we did. From grams to moles, you go ahead and do this, or from moles to grams, you do this, from this to this, you do that. What is it? Do not attempt to memorize it, okay? It's good to become familiar with it. I mean, the best way to go ahead and become familiar with it is not trying to do a photo memory of this thing, no, but doing problems. Every time you do the problems, you're going to figure out that these things, okay, they just come up from arranging your units. That's it. That's all that matters. So that method that I taught you on the first chapter called dimensional analysis, that method is huge in here. And it will help you to do every single setup for these conversions, okay? So I will leave it for this first lecture video up until here, and I will see you on the next one. Bye-bye now.